Last question, I just want to go through this to the end of the lab session, but it's going to take only 5 minutes, I think. So yesterday we have discussed about coding theory. We have seen that this was Hamming code, binary Hamming code. We have seen its length, dimension, its rate. This is okay. We have seen that there were 2 to the 4 code words inside this code. We have seen that its minimal distance was 3. We have enumerated like all the possible code words, and we have seen that the minimal distance, the non-zero code word, which has the minimal distance, its distance is weighted 3. So we have then deduced its detecting capability and error correction capability. And we have seen that we have received this word. And at some point, we figured out that when we enumerated all the code words possible, we have like this code word, 0, 1, 0. Again, I get, if I want the 3 last bits, I have to sum this line with this line. And at the end, it yields 1, 1, 0. And we have seen that this is a code word C, meaning that this is a word that belongs to the code, and that this code word is at distance 1 from the vector we received, okay? But this was by maximum likelihood. This was the closest code word to the one we received, right? And I told you that often this is not the case that we could enumerate all code words. There are 2 to the k possible code words. So basically, it's exponential in the dimension of the code. So we don't want to enumerate every single possible code word, right? So what we are going to do is exactly what we have done before. And that's why we were going to compute the parity check matrix H. And we have seen that it has quite good-looking representation using this H to be minus R transpose, concatenated with the identity matrix of dimension 3, right? So I only take the 3 last columns that I call this matrix R. I put it minus R. We are in binary, so -1 and +1 is exactly the same thing. -1 equals 1 in module 2. Sorry. R transposed. And the identity of dimension 3. Sorry. And what we are going to do is we are going to find the exact same results simply by computing the syndrome of this vector V that we received, right? So if I get my matrix H here, 101, 101, 1, 0, 0. 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 1. Okay, and now we want to compute V times this H transpose, or H times V. And V was 0, 1, 0, 1, 1, 0, 0. Sorry. Yes. This was V. This was H. And if I compute H times V, I have to sum 0 times this column, 1 times this column, plus 0 times this column, plus 0 times this column, plus 1 times this column, plus 1 times this column, plus 0 times this column. So at the end, it's only this column plus this column plus this one, right? Okay, so let's do this. We have S, which is equal to 0, 1, so 1, 1, 0, and 1, 0. 1, 0, 0 gives me 1. Okay, and we're done. We have S, which is equal to 1, 0, 1. And if we look back at our parity check matrix, we can find that this 1, 0, 1 corresponds to the fourth column, right? Here. So I'm done. I know this way that the error is exactly at the fourth position. Explain why S corresponds to the syndrome of the error. Actually, if we look at S, S is equal to H times V transpose, or this is S transpose, which is H times some code word plus an error, E transpose, which is H times C transpose plus H times E transpose. For some C, for some E. But as C is a code word, H times C is 0. So the syndrome of V S corresponds to the syndrome of the error vector, right? Okay. Which is what I wrote here. Finally, retrieve the error and the corresponding message. We have seen that the error was in the fourth position. So the error was actually E equals 0, 0, 0, 1, 0, 0, 1. And when we remove this error from the vector V that we have received, it turned this 0 into a 1. Okay? And if you compared 0, 1, 0, 1, 1, 1, 0, we arrived to this code word C. So we have decoded it correctly. Both methods give the same results. They are both decoding algorithms. The drawback of the first one is that you have to enumerate all possible code words, and you don't want to do this. So usually we use the syndrome decoding algorithm. Okay? And I think that this concludes the lab. Okay? And finally, we can start talking about cryptography using error correcting codes.
I have one question, not directly related, but in this case, G was a systematic form.
Yes.
That's why we were able to easily get H, the parity check matrix.
Yes.
What if, suppose, in general, it may not be in systematic form. So suppose we are given a G, which is not systematic form, and we are asked to same problem. How will we get H from that? Because
I think we had part of this discussion yesterday. It was a question actually regarding the echelon form or the systematic form. When you are given G, it has dimension, it has k lines and n columns, and usually, by definition of k and n is usually bigger than k. You add information to the k bits to get n bits, right? So n is always bigger than k. Otherwise, it would not make sense. So the rank of G is always K, meaning that you can always find K linearly independent rows of G and put G in systematic form.
So we have to do Gaussian elimination first in that case.
Yes, but it's quite efficient.
Yeah, that is.
It's like less than cubic in the dimension.
Yeah, so more generally, we'll have to first convert our G to systematic form by Gaussian elimination, then
well, actually, it's not mandatory to perform Gaussian elimination and have G in systematic form. You can also solve a system of equation, which will give you like the parity check matrix. But I think it's more convenient just to do the work of putting. If you have to do this by n, it's more convenient to put G in systematic form than to solve this whole system of equations. So if I had to do this by hand, that's what I would do, actually. But if you prefer to solve incredibly complex system of equation, you're free to go.
Thanks.
Anyway. So let's keep to the original work of McEliece. So if you don't know McEliece, unfortunately, you won't get to know him. He unfortunately passed away 4 years ago. But McEliece was like an incredible person. He got his bachelor degree in '64, a PhD in '67, and then he got a job at University of Caltech in California. They have a lab, which is called Jet Propulsion Lab. He worked for JPL for some time, and then he became consultant to this lab. He also was like professor of mathematics and a research professor in the Coordinated Science Laboratory in Illinois. Then from 1982, he became professor at Caltech, where he did part of studies, plus he was also consultant for JPL and Sony. And you can see that there is a long story with this Jet Propulsion Lab, and you will see why after. In 1997, he became what we call Allen E. Puckett Professor. So as I didn't know Allen E. Puckett, so I did some research, and it happens that Allen E. Puckett contributed to designing this kind of plane, what we call delta wing planes. And as I work in civil aviation, I thought, oh, it's super cool. But yeah, anyway. He was a professor until the end of his life. And I wanted to give you like a really short quotation from McEliece, one that I love. McEliece was actually a super great professor, and he gave a talk in '89, which was called entitled Safety in Numbers. And he was like trying to explain why error correcting codes are great. And during this talk, I think the very beginning, the introduction was, when I was little, I made a lot of careless errors. I couldn't read my own handwriting. I made spelling mistakes. When I multiply, I forgot to carry. I tried to learn chess, but I always overlooked my opponent's best move. It was awful. Anyway, between my junior and my senior year at Caltech, I got a summer job at JPL. And during that summer, I found out that I could use mathematics to correct errors automatically. For some reasons, it struck a chord. And I wanted to learn all about the subject, and that has turned out the theory of error correcting codes has become a huge part of my life's work. I love the end. I still make a lot of errors, but now I'm getting paid for correcting them. And I like to think that we share this. We have this in common. So yeah, anyway. I wanted to just give you this quote because right after, in this talk, McEliece tried to convince the very large audience that people are already naturally good at correcting errors, at least in English. And he gave the following example. So you are about to participate. This is a black screen. So he gave this very same example back in '89. On the screen, I will make a word of 5 letters appear, and one of these 5 letters is replaced by a question mark, okay? And when you see the word appear and when you have guessed what the word was, you can just shout at the word, okay? You ready? 1, 2, 3, go. Okay, this one was very simple, right? You only had 1 letter missing. It's what we call in error correcting codes an erasure, not an error, but an erasure, right? You know exactly where the erasure is, and you have to correct it. So in this case, it was very simple. On the next example, he then showed that sometimes you don't have an erasure, you have an error that occurred. So now I will show you this 5-letter word, but there is no erasure, there is no question mark, there is an error, and you have to figure out what the error is. You ready? 1, 2, 3. Okay. But somehow, this one was simple, but you can have the sense that it was a bit more difficult than the previous one, right? Okay. And it said that actually an erasure is about half as hard to correct as an error. Okay? But an error can be very hard to correct. Think, for instance, of this word. You will have a 5-word letter, and you are supposed to correct it. You ready? 1, 2, 3. The goal is still the same. Once you found the word, yell it. Okay? 1, 2, 3, go. Okay, we will stop here. So, as you can hear, there's no consensus, right? So, actually, there is no consensus because this one is tricky. This one is one I made on purpose. I chose a word which is at distance 1 from many words. So, of course, it is even more tricky because it's not a very common word, but glade is even an English word. I had to Google for it, but yes, I didn't know this word. But yes, I thought that I made a mistake, but it is an English word. Glade is an English word. Blade is an English word. Grade is an English word. Glide is an English word. Glare is an English word. Maybe there are other at distance 1, right? So you cannot accurately correct this error. But sometimes even an erasure is hard to correct. Okay, you ready? 1, 2, 3. Yeah, I was sure Peter was about to shout stout. Yes? Okay, so yeah, indeed, there are several possibilities. There are scout, shout, snout, spout, stout. So yes, okay, you have an erasure, but still here again, you have several possibilities. Well, actually, we are not getting interested longer in this part of this is life's work. We are going to jump several years later when McEliece was still in Jet Propulsion Lab, but he became interested with the work of Diffie and Hellman about, this famous paper, New Directions in Cryptography, which is cited like 20,000 times. And in this paper, Diffie and Hellman suggest that maybe it is possible to construct an asymmetric crypto system, okay? And actually, McEliece was really unfortunate by that time because amongst a couple of months, Rivers, Shamir, and Edelman came with this solution that we know all as RSA. But in the very same year, McEliece proposed a public key crypto system based on algebraic coding theory. I removed the date and stuff like this. This is a very short paper. I think the paper is like 3 pages. The first pages is half part blank, and the last page is the third one. It's only a reference. And in the reference, you can see RSA already cited. Maybe it was the first one to cite RSA. I don't know. But anyway, in this paper, McEliece suggests to actually use binary GOPA codes. We are not getting into what are binary GOPA codes because I will need a lot of mathematics involved to define probably binary GOPA codes. But anyway, it suggests to use some codes to construct a public key crypto system. And from what I have said before, you already have a feeling of how this is going to work. And so here is how it is going to work. So the setting up phase of McEliece is I want a generator matrix of a binary GOPA code C. I denote this by G, which is a K times N matrix. And this code C should be capable of correcting up to T errors. Okay? And whenever I own this matrix G, I have the associated efficient decoding algorithm, which I denote by decoding of C, D sub C. Okay, are the notations clear? If it's not, do not hesitate. And eventually, to help you follow what is the public key, what is the private key, what is the randomness, I give this legend: what is in green is public, what is in red is private, what is in blue is randomness. Okay? So, we have still our 2 favorite characters, Alice and Bob. Alice start by invertible matrix over F2 to the K times K. So it's a K by K invertible matrix over F2. Okay, she also generates at random a permutation matrix of dimension n, so it's an n times n matrix. She takes her matrix G, which she has to keep secret because it gives the decoding algorithm, and she wants to publish like a disguised version of the code. So she will compute S times G times P. We denote this tilde, G tilde, and she publishes G tilde and T, the capacity of the code. Okay? What is really, really, really super important is that G tilde is a disguised version of the code, and G tilde does not give you the decoding algorithm, the efficient decoding algorithm. If you're trying to decode with G tilde, you're not going up to T errors. Okay? So if you want to try to make a connection with lattices, G is the good basis of your lattice, and G tilde is the bad basis of your lattice. You can sort of just encode with G tilde, and you can do much more things with G, the original G. Okay? So Alice publishes G tilde and T, the capacity of the code. What Bob does when he wants to encrypt message M, so it's a binary message of k bits, he samples uniformly at random an error E, such that the weight of E is less or equal to T. In practice, you always want the weight of E to be equal to T, because you can correct T errors, and the problem gets harder for an adversary if the weight of E is maximal. So Bob has now M, E. What he's going to do is encode M with G tilde. So this gives M times G tilde, and he will add on top of this his error E of weight T. Okay? So this gives the ciphertext C, and Bob sends C to Alice. And we have a complicated formula to decrypt, which is I begin by multiplying right by P minus 1. Then I decode this product. This gives me C tilde. And finally, I multiply C tilde by the right by S minus 1. Okay? So I have a question for you. What about the correctness of the scheme? The correctness of the scheme is if I have a legitimate Bob that correctly follows the encryption algorithm, he sends C to Alice, and Alice correctly follows the decryption algorithm, is she going to find the original message of Bob? In other words, is the scheme correct? Do you have any idea of this? Maybe I've just show you the formula here, so maybe we can discuss a bit about this. But Cp minus 1 is M G tilde plus E times P minus 1, right? But G tilde, it's M S G P plus E times P minus 1. So it's equal to M times S times G times P minus 1 plus E times P minus 1. So of course, this part here simplifies. And we have M S G plus E P minus 1. Okay. Just for a moment, let me help you by writing tilde M equal M times S. Okay? Just for a moment. So in the end, I have tilde M times S, times G plus And let me write till E equals EP minus 1. Okay, so at the end, when I compute CP minus 1, what I get is some message, which I call M tilde, times the generator matrix times some error. Okay, but here the generator matrix is G, it's not G tilde, it's G. So I know the efficient decoding algorithm associated with G, right? How many errors can I decode with this algorithm? T, up to T errors. So basically, I will be able to decrypt this if, and only if, this term has weight less or equal to T, right? Is this the case? Why is that? You're perfectly right. E tilde is EP minus 1. P is a permutation, so P is invertible. And its inverse is also a permutation, right? And the Hamming weight is defined as the number of non-zero coordinates in some vector. So if E has weight T, any permutation of E will also have weight T. So basically, what makes McEliece work is that E tilde has weight less than or equal to T. So I can apply this decoding algorithm, which I denoted D sub C of this. And this will give me back the message M tilde, this one. Okay? Any questions so far? No question? Okay. But remember, M tilde is not the original message. It's M times S, which is why at the end I have, oh yeah, okay, I denoted C tilde. In the slide, C tilde is my M tilde. But if I do M tilde times S minus 1, which I can do, as it chooses S to be invertible, this will lead the message, the original message. Hence, the correctness. Okay? Well, you know McEliece. So, yeah, we'll see for the last session. It's not mandatory. Anyway, I said earlier that McEliece was quite unfortunate when back in '78 because he was among the first people in the Earth to find like almost the first crypto system, asymmetric crypto system. From centuries ago, all the cryptography was symmetric cryptography up to 1976 and then 77, 78, where RSA was discovered, was invented, and we also have McEliece in 78. But we could have been using McEliece instead of RSA for the last 3 to 4 decades, but this has not been the case. Simply because in McEliece's original proposal, if you look at the parameters he suggests 2 parameter sets, one for 64 bits of security, and I think one for, I don't remember exactly, I think this is 96 bits of security. But honestly, by that time, 64 bits of security was completely enough. We were back in '78. And roughly, the RSA paper suggested keys for the same security level of 1024 bits. Okay, if you wanted to use RSA back in 78, you only had to take P 512 bits, Q the same, so you end up with a modulus of 1024 bits. And if you want to do the same thing with McEliece system, you have almost a public key 3 orders of magnitude bigger than this. So usually I say RSA was 10 to the 3, and McEliece was 10 to the 6. Back in 78, 1024 bits was kind of, it was okay. It was quite expensive, 1 kilobit at this time. But it was okay. If it's for security, for authentication, you know, it's a lot of good properties, so we can accommodate for 1 kilobit. But 1 megabit, it was 1,000 kilobits. It was completely out of question to use something which would cost a megabit back in 78. Now the situation has completely evolved, and now it is okay to use large keys. So yeah, anyway. Like yesterday, I thought that it would be like cool if we take a few moments like to just don't rely on the math and try to give concrete values and try to see if McEliece work. So if I think it's cool. If it goes too slow, you can feel free to tell me. If it goes too fast, feel free also to tell me. So what I suggest is to give you S, G, and P. I am a list. I generated my secret key, SGP, and we are going to simulate like we want to use McEliece with this kind of handmade version of McEliece. So the first question for this lab is, show that S is invertible. There are several possibilities for this. Can anyone tell me how to do this? Excuse me? Yes, we can compute the determinant. Okay. There are several methods, but at some point, we will need S minus 1 when we want to do M tilde times S minus 1. So let's assume that the lecturer has correctly configured this instance and that S is invertible. I think we are going to try to directly invert S, if it's okay for you. Otherwise, we can compute the determinant. But if it's not the case, I can take 2 minutes just to do it. No? Okay. Again, there are several methods for inverting a matrix. The one I prefer is to put it in the. Sorry? Yes. Look, it is easy to compute. See how easy it is? No mental efforts whatsoever. But yeah, of course it is easy to compute. So yeah, anyway, this is a cheating method. This is a computer scientist method. If you want to do this by n, what you are going to do is you put this matrix here, you want to inverse. You put identity here. And the goal of the game is to make this identity matrix goes from right to left, and then magically it will appear S minus 1 here. And this one is actually quite easy, because if you sum up these two lines, you will get 0, 0, 0, 1. So that's what I am going to do on the last. And I will put this result in the last line. Okay? So in the last line, I will have 0, 0, 0, 1. And the corresponding part on the right side is the sum of these two lines, which is 0, 1, 1, 0, 0, 1, 1, 0. There is also another one which is easy. It's this line plus this line. It will give me only a 1 in the third position, so I will put this result on the third line. And this plus this is 0, 1, 0, 1. Now that I have the third bit here and the last bit here, I will sum these two with this one, so that I only have this one left. So 0, 1, 0, 0, which is 1 in the first position, 0, it is the sum of these lines. And finally, which one can I take? This one. This one, so I will have like this. This is 0, 0, 1, 0. And I have to sum it with this one. 0, 0, 1, 0. So this will give me this. And I think I'm done. I need to check this, but 1001, 1001, 1011, okay, 0101, 0110. Okay, I'm still good at inverting that matrix by hand. Okay, so yes, it is easy, but still longer than with Sage, for instance. Sage is an overlay of Python, which is very useful when you want to use already built-in functions like for factoring, for yes, this stuff here is the Galois field of characteristic 2. It's a Galois field of 2 elements. It's F2. It's a finite field of 2 elements. Okay. I put the matrix. I ask for S minus 1. I could also have asked for the determinant of S, which obviously must be 1. Obviously, I am working in F2, so it's either 0 or 1. If it's 0, the matrix is not invertible, so it's 1. You can do several steps, also including matrix multiplications so far. So, yeah, okay. So now we have S minus 1. Yes, explain why P is invertible. We have already said that. P is invertible because P is a permutation. As a permutation, it has an inverse permutation. And so as P is the matrix representation of the permutation, the inverse permutation has a matrix representation too, which is P minus 1. Okay. So now, the longest part, we have to compute S times G times P. You know how to do matrix multiplication. We just have G tilde equal to this. Trust me. I have not done this by hand. I asked Sage to do this. So now we want to encrypt the message M equals 0101. Compute X equal M times G tilde. So we are going to take this G tilde, and as we want 1, we are going to sum up this row with this one, 0, 1, 0, 1. Okay? So this should give me 1, 0, 1, 1, 0, 1, 0. Looks like, sounds like what I said. Yeah, okay. Deduce the ciphertext. We know how M G tilde, we only have to add the error. Yeah, I did this in a rush, so I didn't put the error I wanted to add. I think it was in the 5th position. I don't remember exactly what I've done. No, it was in the fourth position. It was in the 4th position. This was this error, okay? The error is in the 4th position. Compute S minus 1. Okay, we already have done this. Let's use Sage, for instance. Compute P minus 1. Are you going to compute P minus 1? What's P minus 1? To inverse S, I prefer using Sage. To inverse a permutation matrix, I prefer to use math. Because a permutation, a matrix representing a permutation, lies in what we call the orthogonal group, meaning that a permutation matrix satisfies P times P transpose equal identity. With this equation, we know that P minus 1 is P transpose. Okay? So we don't have to compute P minus 1. We only have to look at P and transpose it. Okay, compute Y times CP, Y equals C times P minus 1. Okay, so what's C again? C is equal to 0, 1, 0, 0. 1, 1, 0, 0. Sorry. Yeah. Sorry. And I have to multiply this one and this one. If we sum this column, we can see that we have 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0. This should be this. Okay? Let's check. No, I made a mistake. Why is that? By P minus 1. So basically what I have to do is see P minus 1. I told you that this is C P transpose. And we can also write this P C transpose. Okay? So what I will do is simply draw my matrix P, draw my vector C here, and sums the column of C instead of the line. So I have the first, fifth, and sixth column. The secret key again. We have that Y, which is equal to CP minus 1. We have, when we developed this before, we ended up with M times S times G plus E P minus 1. And in McEliece scheme, the secret key consists of S, G, and P, or even P minus 1, as P minus 1 is P transpose. Okay? So this is the relation you have between CP minus 1, which is, I call it Y, and the secret key here. Now, of course, we want to decode what we have received here and multiply by P minus 1. So we are going to use H. I took the same matrix G as before, I think. And so basically, we know now that H is going to be this part, the last part, transpose, concatenated with identity. So if I want to write H is going to be 110, 011, 111, thank you. 101. Okay, and identity. And now, oh, I erased Y, sorry. I shouldn't have erased Y. It was 0, 1. Y was this one. So now I want to compute the syndrome of Y. This is what we do when we decode Y. So we compute this vector times this matrix. So we have the first two columns plus this one, which gives us 0, 0, 1. Okay? So the error becomes in the last position. So we have that E prime equals 0, 0, 0, 0, 0, 0, 1. And hopefully, E prime is equal to E p minus 1. So I think this is not going to work. I don't know where I failed exactly, but yes, I think I have failed. So basically, what we have is that the error here is in the last position. So when we want to correct Y, we remove this bit, and we do not land on the original message. So I think I've made this too fast. Oh no, I did not finish. Sorry, excuse me, I did not finish. So I will erase this part and say that we have this C tilde, which is equal to 1, 1, 0, 0, 1, 0, 1. Okay. But as I said, and this is important here, when I apply my algorithm, my decoding algorithm should give me a word of 4 bits, not 7. Otherwise, I won't be able to multiply by s minus 1. And here, since the generator matrix G is in systematic form, I know that the message here is represented by the 4 bits, the 4 first bits. Okay? So the CTL I get is not this whole stuff, the Y plus the error, or minus the error. It's only the 4 bits here. So actually, CTL is this vector. And to finish the equation, I have to multiply this by s minus 1. And s minus 1, multiplying this by s minus 1 is just taking the sum of the 2 first rows. And if I take the sum of the 2 first rows, I get 0, 0, 1, 0. 0, 0, 1, 0. Yes, it actually fails because my original message was 0, 1, 0, 1. I think, or 1, 0, 1, 0, I don't remember. 0, 1, 0, 1. Okay, so I have a homework to do for tomorrow, is to correct and tell you tomorrow what went wrong. I'm sorry for this. I have worked this example, but I think maybe this should have been the correct value. I don't know what I have messed up, but this has been the correct value. Y should be equal to this. Let's assume that we have found this Y. 0, 0, 0, 0, 1, 1, 1. Then, when we compute the syndrome, we take the sum of these 3 last rows. We get 1, 1, 1, which is an error in the 3rd position here. So we had this error to Y here, and to decode, we take only the 4 first bits. So we have 0, 0, 1, 0. And if I multiply 0, 0, 0, 1, 0, I found back my M equals this one. So yeah, basically the error, I did my homework for tonight. The error I've done is when I multiplied C by P minus 1. I don't know what I tried the shortcut, but it failed. I'm really sorry about this. But yeah, just transpose P. and compute C times P transpose. Okay, and you will get Y equals to this. I'm quite confident this is a good result because I have implemented this in Sage and this was the result, so yeah. Anyway, so this is a good news. When you implement this correctly, McEliece actually works. Okay? Right. Is there any question? So I told a bit about McEliece crypto system. I told you also about the key size problem. I didn't tell you yet about the security. Okay? Even if the public keys in McEliece are 3 orders of magnitude bigger than RSA's, it is still competitive in terms of efficiency. It might sound like a huge claim, but when actually you are working with McEliece, you are only doing linear algebra, you are making matrix vector multiplication in binary. So everything goes super fast. Okay, but you have to do like, you have to go through the thousands of columns and through the 500 lines. It's about, in McEliece, you have approximately k equal 512 and n equal 1024, which gives us 500,000 bits, okay? Roughly this. In RSA, the keys are kind of much smaller, only 1024 bits. But when you are working modulo a number of 1024 bits, it's that basically you are working modulo this number. Okay? And in RSA, you have this relationship C equals M to the E mod N. So this is a 1024-bit number. This is a 1024-bit number if you don't take E equal to 3 or 65,537. And this is a 1024 bits number, meaning that you have to do modular exponentiation of with arithmetic of 1024 bits number, which is kind of really slow. In comparison, classic McEliece, sorry, it's only linear algebra on the binary field, so this is super efficient. But McEliece has huge key sizes. So yeah, anyway, what about the security? What is special? No, here, you're completely right. That's actually a good point. Here, I did McEliece on Hamming code. Don't do this. It was just a toy example. This has 0-bit security or something close to this. Okay? You have to use binary Gopak code if you want to use McEliece in the real life. Excuse me? When we use Hamming code, for instance? Yeah. Actually, if you're not using binary Gopak codes, I will show this in a few slides. If you are not using binary Gopak codes, there is a high chance that the family of code you are using is distinguishable among random codes. Meaning that given this disguised version of the code, one can find back the correct version of the code, hence the decoding algorithm. Yeah. From your public key kind of leaks your secret key, yeah. It's not that simple, but yes, it works a bit like this. And it is possible to find back the private key. Yes. So before speaking about the security of McEliece, I have to introduce the syndrome decoding problem. And for this, I have a problem statement which is the following. I consider S to be a syndrome with n minus k bits, I consider a parity check matrix, H, and I ask you to find x of n bits such that x, the syndrome of x, is equal to S. So, question, is this problem hard? If you need a hint, you have already been asked this question. If you need a second hint, it was by Alice. Does anyone have an idea? I didn't hear you. H and S are? They are, yes, it's an instance of the problem. I give you H, I give you S, and you have to find back X such that H times X. Yeah, okay. Okay, so your answer would be, is this problem hard? No, easy. Right. It's only linear algebra, and actually, the simplest way I can think of is that you sample at random n minus k columns of H. You get a square matrix, it's a matrix of H. You can try to invert it and solve the system. It's like a Gaussian elimination. Right, okay. So now, I just put an additional constraint on this problem, and I asked it's exactly the same, but here X should have relatively low weight. Is this problem hard? Yes, it's the same as for lattices. The problem becomes hard and cryptographically relevant or interesting. Well, and it turns out that for McEliece security, you have two aspects. McEliece security is clearly, I don't know how clear it is, but it's based on the honest of decoding efficiently a seemingly random code. Okay? You are provided an instance of McEliece when you intercept a ciphertext. You are provided with an instance of McEliece where you know the public generator matrix, G tilde, you know the error correction capability of the code, T, and you have just seen a ciphertext. And you want to decode the ciphertext to retrieve the message, but you only know the disguised version of the code. So to decode efficiently, you need a polynomial time algorithm that corrects sufficiently many errors that can remove the E part. And you also need that when you want your security to hold, you do not want your public key to reveal like the structure of the code. Which was your question, by the way, I think. So, yes, actually, we'll get back to these two assumptions. But here are the parameters. It was not 64, it was 62 bits. You can see that you have n equal 1024, k equal 524, and d, the minimal distance, was 101. And this yield 67 kilobytes key sizes. Well, so the public key size, G, it was like really impractical back in '78. Now in the 2020s, it's like doable. And by the way, and I think I will spend a bit more time on this approach. We have a quite nice way to like immediately shrink the key size of McEliece. It's to use Niederreiter's approach. And I will spend a few more minutes on this. I think we're fine. And said, you have to use G, you find S, G, P, you disguise the code, and you take an error vector, you add this error vector to the encoding of the message, and then you can decode, and everything goes well. But now you know that G has also another representation for the same code, which is its parity check matrix. If a word is a code word, then its syndrome by the parity check matrix is 0. And so I said earlier then that the parity check matrix is the generator of the dual code, right? But it turns out that you can use like a dual version of McEliece using this parity check code. This parity check matrix, sorry. And the idea, why are we going to do this? It's because if we want to use G, then we will have to fully represent G, meaning that we are going to give K times N times the binary logarithm of 2, which is 1, K times N bits of information for representing the public key. If you want to use H for this crypto system, you will have to fully represent this matrix, which is N minus K times N. So this time, you will need N minus K times N bits. And as this does not make a lot of difference for the first set of parameters, because roughly K is equal to N over 2, this has a lot of sense for the second set of parameters, right? Because here you have K, which is roughly 3/4 of N, sized by 1/2 N, right? You have like K, so N minus K is roughly this, with N roughly equal to 2000. So yeah, it makes a lot of sense, right? You divide the key size by 4, and it's completely free. So this only came 8 years after McEliece. Okay? So in the same way, you will have like an H here. You will provide like a disguised version of H. And when Bob wants to encrypt M, this time, he will encrypt like M. He will choose an error E, which is an F2 to the N, I think. Yes. So Bob has to map his message, which is K bit long, to a N bit long error of weight such that weight of E is equal to T. Okay? So in order to encrypt, Bob has to map a message M of K bits to a vector of N bits of weight exactly T. Okay. And then the ciphertext is simply the syndrome of the error. He sends a ciphertext to Alice, and Alice decodes the ciphertext. This gives her the error that Bob chose, and she applied the inverse mapping to find back the message. What's important here is that you have to design a one-to-one mapping between words of dimension K and low-weight vectors of dimension N and of weight T. Okay, you have to design this one-to-one map. It's not that complicated, but it's a bit of complexity that adds on top of the system. But really, if you are very demanding on the key size, it allows you to shrink the key size by a factor 4, which is not negligible. Okay? Right. So if k is greater than n minus k, then we can rewrite McEliece using the parity check matrix H. You obtain Niederreiter crypto system. The only exception that back in 1986, Niederreiter suggested not to use binary GOPA codes. He suggested to use generalized Reed-Solomon code. We will see that this was a terrible idea in the next slide. There is another strategy to reduce the public key size, and which is also heavily used in lattices. It's to use more structural codes, where actually your public key has a compact representation. And usually we use like quasi-cyclicity or working in ideals or in quotient rings or stuff like this to benefit from the fact that you can represent generally a full matrix using only one vector. Okay, and then you can gain a factor up to k, meaning a factor up to 500. Okay, so we are now back to the very strange problem that the public key, the generator matrix of the code should not reveal the structure of the code. And probably, if McEliece's approach has one drawback, this is this one. Because McEliece was published in '78 with binary GOPA code that were suggested. The next improvement upon McEliece was Niederreiter's, which was a dual version of McEliece, and it's then suggested to use generalized Reed-Solomon codes. And sometimes later, there were two people, Sidelnikov and Chestakov, who arrived with a cryptanalysis of Niederreiter's approach, not fundamentally on this approach, nor the small technicality here to map a message to an error of weight t, but really because they were only looking at the public key and they were able to retrieve the structure of the code, meaning that generalized Reed-Solomon code were not indistinguishable from random codes. Okay, they managed to recover the structure of the code and then to decode it. Eventually, some of the two people, one person of the two people before Sidelnikov. Oh, sorry. What? Sidelnikov, shortly after, proposed to use Niederreiter's version with Reed-Muller code. Then other proposal was made with algebraic geometry code and also subfield subcodes with subcodes of generalized Reed-Solomon codes with quasi-cyclic BCH codes. But it turned out that there was a terrible attack, which brings square attack. When you consider the square of code, meaning that when you have a code word here, C, which is equal to C0, C1, so far so on, up to Cn minus 1, what I call the square of a code, if this is C and you have C prime, which is like C0 prime, C1 prime, so far so on, C n minus 1 prime. If you want to do like C star C prime, you will have coordinate-wise C0 times C0 prime, C1 times C1 prime, etc. Okay? And actually, when you do this, and when you look at the code which is generated by the product of the code words of the code, there are some properties that this code has over the dimension. Okay? Meaning that, maybe I can give some more details on this. usually we denote by C square or C star C. The code were generated by C star C prime for all C C prime in the code C. Okay? This is a code, and this code has a dimension. Excuse me. You will see. You will see. It happens that I have a little doubt on the exact dimension, but it happens that when you look at the square, the dimension of C square, it should be either maybe 2k plus 1 if C is random, and something else if the code is not random. And this something else would be something different, whether it's a GRS code, an algebraic geometry code, or, but it won't give, it will give you something different from 2k plus 1. Okay? And actually, this attack was like terrible because at that time it only worked like on one scheme, but it also eventually worked for other scheme later proposed. But there were also attacks on regular codes, on algebraic geometry codes with genus 2, less than 2, sorry. Other quasi-cyclic alternate codes were proposed. Wild Göka codes were proposed. And as you can see, even at some point, each proposal was cryptanalyzed. Up to 2012, where these four people, Raphael Mizowski, Jean-Pierre Tillich, Nicolas Cendrier, and Paulo Barreto, proposed quasi-cyclic moderate density parity check codes, MDPC, QC MDPC. And basically, I think tomorrow I will give some details about this scheme, because this scheme is roughly byte. Usually, at the very beginning of the byte submission, there were three versions of the scheme: byte 1, byte 2, byte 3. I think this one was byte 2. I think byte 1 was K, submitted it was published in 2016. And the last version of byte 3 was Ouroboros, which was published in 2017. But eventually, at some point, NIST asked for the byte team to reduce their different version, and we had like long discussion to finally select one version of byte, and this was byte 2, which is now called only byte, and this is QCMDPC, with several like improvements, but roughly this is QCMDPC. And QCMDPC, MDPC stands for Moderate Density Parity Check Codes. What moderate density parity check codes means is that you look at the parity check matrix and you look at the non-zero coordinates on each line or on each column, and it only has a moderate number of non-zero entries. When you say moderate, roughly we have something which is the weight of each column is something which is a big O of square root of n, right? MDPC. And yeah, eventually other attacks. And as you can see, with this approach, changing like the family of code you are using to try to improve the correction capability of the scheme, it has always been a bad idea, except for QCMDPC. But with QCMDPC, there were also some other arguments which makes that It's not completely comparable to McEliece. But anyway, McEliece approach, Niederreiter's approach is a dual version of McEliece, but Niederreiter suggested to use other code. If you take Niederreiter with binary GOPA code, you are as safe as McEliece is. Okay? I'm not saying that Niederreiter's approach is doomed to fail. I'm just saying that Niederreiter and McEliece, both instantiated with binary GOPA codes, are equivalent. If you take Niederreiter with anything other than binary GOPA codes, it will fail. Okay? And then some decades later, you had this QC and DPC codes, but I will talk extensively about this tomorrow. Okay? Yeah, anyway, so roughly... Sorry? Oh, yeah, can you use the mic, please?
What does quasi-cyclic mean? Like I don't know the meaning of the word quasi-cyclic.
Quasi-cyclic, okay. Let's assume this is my parity check matrix. If this matrix had been cyclic, I would have the first vector. I could take this vector and make cyclic shifts of the first line to get the other line. I take the first line, I shift it, everything that goes outside the range is put on at the beginning. This is cyclic. Okay, this will yield a square matrix. You don't want this for a parity check matrix. Polycyclic, it's almost the same, unless that you use blocks. You have usually one block here and another here, and cyclicity applied to each single block, meaning that you do the same here. This overlap on the second part, so you put this one here, and so far, so on. Okay, and you do the same for the second part. Quasi-cyclic means it's not cyclic because otherwise you would have to take the first row and shift it. Here it's quasi-cyclic because you have to consider cyclicity per different row. This is quasi-cyclic of index 2. You have two blocks. You could have quasi-cyclic of index whatever. Okay. Mike?
There was a QD on the previous slide, like QC and QD, like in the previous slide.
QC
and QD.
Oh, quasi-dyadic.
Sorry?
Quasi-dyadic. It's even more complicated. There was a submission to NIST which used quasi-dyadic codes. I think it was DAGs. And eventually, at some point, I think there was an attack by Barelli and Couvre. I don't remember the year. On DAGs, and I think they attacked like quasi-dyadic codes. I don't know if they attacked exactly quasi-dyadic codes or just submission, but yeah, QD is quasi-dyadic. It's a bit more involved because you are working no longer in mode 2 but in mode Q. You are not working on the same, well, because you're working mode Q. When you do like f2 to the x over the polynomial x to the n plus 1, actually, sorry, it's not 2, it's mod q. When you are working mod q and you reduce mod this polynomial, everything that goes up here, you have to put it at the very beginning. But if it was like, I don't know, 3, it becomes -3. Okay? Whereas when you work in binary, 3 and -3 are the same, it's 1. So you don't have this notion of minus. Okay. But yeah, QD was dyadic, sorry. Yeah, anyway, so if you want to use McEliece approach, use binary codes. For the moment, it seems to be safe. They seem to be safe. Maybe at some point we will find out that they are not safe. You can distinguish binary go-back codes from random codes. Maybe not. We have evidence, like if you consider binary go-back codes of very high rate, K over N rate. If you consider binary go-back codes of very high rate, then you can distinguish them among random codes. It was used for a code-based signature back in 2001, which was broken due to this. Yes, okay. And the other thing, and maybe I'm going to stop here, is that in order for your scheme to be secure, you don't want to be able, like, to decode efficiently any random code. Basically, this is like rephrasing that the syndrome decoding problem should be hard in practice. And this is the case because when you look at the syndrome decoding problem, best known attacks for the syndrome decoding problem are called